Hello, I'm Rahul with Team 22105 Runtime Terror, and their robot here has lots of mechanical complexities with this pocketed telescopic box tube extension, a level 3 hang using a drivetrain powered takeoff, and a very simple intake allowing them to achieve really low sample cycle times. Learn more on Behind the Box. Okay, hello team, Runtime Terror. Now, I see you guys have this really complex robot, but let's start off by talking with your general game strategy and design philosophy this year, and why you chose to focus on only samples rather than doing both or only specimens.
Yeah, so like you said, our game strategy this year was to be able to do just the samples at the highest level. That way we're able to specialize within our alliance and we don't slow ourselves down by being more of a generalist robot. So when we're able to specialize in our alliance, we can score just the samples from the submersible to the high bucket, while our alliance partner can focus on all of the specimen scoring side of things. And this allows us to maximize our points overall and score the most points possible.
That's great. Now another question I had is, why do you guys opt for the pivoting architecture rather than some sort of transfer system where both sides have had many teams go for them?
Yeah, so having a pivoting architecture has many advantages over a transfer system where we can combine our intake and outtake into one mechanism where we simply intake and then pivot up to deposit in the high bucket. And another advantage of this is transfer systems can be quite slow and can reduce our cycle times. So when we have just one intake and outtake, just the pivoting takes up all of our time, and it reduces our time down to very fast cycle times of just 4 to 5 seconds.
Great, now let's just jump straight into this robot. I see you guys have just so much pocketed aluminum on this robot in general, in your box tube, your whole drivetrain superstructure. Why don't you guys talk to me about all this aluminum superstructure and your drivetrain in general this season?
Yeah, as you mentioned, we do use a lot of pocketed aluminum, and that's because aluminum is really strong and is very light. Our robot is only around 22 pounds, which helps with our cycling time, and also the strength of the aluminum helps when we have to play defense, and it's very durable. For our drivetrain, we use a simple belted mechanism drive, and we also use the new grip force mechanism wheels that help with acceleration and our speed. We also have sprung odometry wheels for our autonomous.
Great. Now I think your drivetrain is nice and simple, but that belted mechanism drivetrain, which many teams opt for, something that caught my eye here is this sweeper sort of attachment. Why don't you guys walk me into what that is and how that's helped you this year?
Yeah, so we have a sweeper at the bottom of our robot. It basically sweeps from underneath the submersible and clears the way for our intake so we can pick up samples more easily.
Great, thank you so much for that. Now, let's just talk about the main highlight of your robot, your box tube extension. It's just so fast and so elegant with its ISO grid pocketing. Just walk me through every component of it and what things you've learned from doing it this year.
Yeah, so our box tube extension is our custom pivoting and extending box tube is the main system of our robot, where it's fully custom pocketed aluminum, where we had a team 5064 from North Carolina helped us with the pocketing, and we use custom 3D printed bearing supported inserts to give us rigidity in all 4 directions of our box tube. And this is much lighter compared to linear slides and allows us to reach those really fast cycle times. Now, on top of this, many issues that came up with our box tube were we were stringing. So stringing with the box tube, you have to have cascade stringing. So we actually have 4 separate strings where they're cascade strung. So all of the entire box tube extends all together at the same time. So each stage extends simultaneously. And another difficulty with building box tube is these bearings need to be toleranced very well and need to fit our box tube very well, so we really achieve that rigidity in all 4 directions.
Great. No, I think your box tube is just so cool with all the pocketing and stuff like that. So what exactly played into did you guys think of the box tube mechanism immediately when you chose that pivoting architecture, or were you more considering pivoting linear slides versus box tube and you eventually decided on a box tube system?
Yeah, so pivoting linear slides, transfer linear slides, all of that came through our brainstorming, but we decided on the box tube system because something like pivoting linear slides, first of all, it takes up a lot more space, and also it's a lot heavier, and also it doesn't give you rigidity in all four directions like the box tube. And so we decided on a box tube because it gives us the advantage of having no transfer and the speed of having no transfer, but also gives us rigidity and a lightweight robot.
Great. Now, why don't you guys walk me through how your extension and pivot are powered? I see all of the motors are mounted at the bottom of your robot, and I think it's quite cool how you've packaged all of the extension and that center spool and the pivot axles. Just walk me through all of that and how it works.
Yeah, so our extension motors are right here inside our robot, and they go through this belt, which connects to our PTO system for hang, and then also connects finally all the way through to this central axle. This central axle is coaxial with these go tubes, and these go tubes are attached to these pulleys right here, which can actually pivot our full robot, and this powers the spool in the center, which extends and retracts our robot.
Great. Now, thank you so much for this box cube. I think it's really cool how fast, and it's really contributed to those really tip-top cycle times for your system. Now, let's just walk into that hang system. Why don't you guys walk me into why you chose to do a PTO this year, what benefits it is, and just how your whole system works with that level 2, then level 3 ascent?
Yeah, first of all, in order to achieve the first level of ascent, we just have a simple system where we have 2 sprung hooks attached to servos that just pull the robot up to the first climb. Then we also have our special PTO system, as you mentioned. So the main goal behind this was to improve the torque when hanging, but we also wanted to keep speed when we're depositing and picking up samples like in a normal cycling time. So the way we did this was we had a servo linkage attached to a gear that drops down and physically connects all 4 of our drivetrain motors to our 2 extension motors. And this helps give us enough power to pull the entire robot up to its 3rd level ascent in under 6 seconds.
Yeah, so it connects like you said, it connects our drivetrain to our box tube extension. So if you see, our box tube moves as our drivetrain moves forward. And that gives us the torque we need for that level 3.
Great. I think that's really cool how while you drive forward, it's able to retract the box tube, and I think that shows how your system's able to function. Now, is there a reason you guys chose to do your PTO-based hang rather than just using your regular extension motors, and why did you guys go across with this decision this year?
So as I mentioned earlier, speed was a really big goal in our system this year. So in order to achieve speed, you can't have too many motors at one time. So we have 2 motors on our extension, and that helps going really quickly in our cycling times, and we can maximize the amount of time for cycling enough samples during teleop. And then in order to combine 6 motors, it gives us we have the 6 motors for our hang make our hang really quick, so we can maximize the amount of samples placed and also have enough time for hang.
Great, I think that's really cool how you guys are able to switch between low torque and high torque between teleop and hang. Now, I see you guys mentioned that 6 motors things. How did you guys decide upon that optimal gear ratio for your hang? Did you guys have any issues with drawing too much current with 6 motors, blowing fuses, or anything of that sort? Or did you guys have any iterations with that PTO in general?
Yeah, so with our PTO, we've changed this gear ratio a few times because we wanted to have our PTO super fast to be able to reach it be able to reach level 3 as fast as possible. But at the same time, you have to balance that with having enough current draw from the battery not to like explode your robot. So we also so that's also another factor in wanting to have 6 motors, 4 drivetrain, and 2 extension to pull up our robot, because it's able to do it much faster and also helps with battery and current draw systems.
Great. Now, I think let's just hop into your intake. I think it's very cool how you guys have this very simple intake, just 2 wheels off a servo. How did you guys come across this intake, and how has it been for you so far this year?
Yeah, so our intake is a dual wheel active intake where it's very small, but it's also able to be an active intake, and it's able to retract the sample very, very quickly. And so we wanted the advantage of an active intake without like all the bulk, so we were able to settle on a design like this. Some of our iterations with the intake was previously we had a differential claw system, which also allowed us to score specimens, but we switched to an active intake to be much faster.
Great. Now I think it's very cool how as soon as that intake touched the sample, it automatically went down. Now one thing that caught my eye here is that the boxtube system seemed to immediately retract when the sample was in your intake. Is that a driver controlled feature, or do you have any sensors or automation allowing you to do that?
Yeah, so that's actually pretty cool where you can see the light actually coming from it, where we have a color sensor in here that detects that we have a sample, and also detects if it's an aligned specific sample, and retracts automatically, which saves time for the drivers.
Great. I think it's really clear in how fast your teleop cycles are, just how much driver controlled optimizations you guys have spent. Now, I think we've done a great job in going over all of the mechanical components of your robot. I see you guys have this really tiny camera here. Why don't you walk me into what that camera is used for and how that functions in your autonomous period?
Yeah, so in our autonomous period, we use Easy OpenCV on the camera, where we would draw blobs around the yellow samples. So we would group them all together, and then we would kind of strafe to the best possible blob of yellow samples and just simply extend and take the sample. And yeah, it's pretty consistent.
No, yeah, I think one thing I'd like to ask is, I see you guys have put your camera, two things caught my eye. One, that it's tilted pretty far down, and I'm wondering how much of the submersible are you able to see, and is that specific to the camera? And two, why did you guys opt to put the camera on your robot rather than on your extension? I think I've seen both sides throughout this year, some people doing it on the extension or some people doing it on the robot. What decisions kind of played into your choice right there?
Yeah, so for number one, we're able to get like a pretty good view of the sub, especially since this has a 160-degree FOV. But for number two, we actually used to place our camera over here, and we had some problems getting like a good view of the sub. So, and we also hit it on the sub bar, so we decided to move it and mount it on the drivetrain over here.
Great. No, I think it's nice how you're able to see a lot of the sub with that 160-degree FOV. Now, just going into some general questions, I see you guys have these really fast teleop cycles that I think a lot of teams can take inspiration from, almost 4.5, 5.5 second cycles. How have you guys achieved such fast cycles, and like how has that evolved over time in that season? What have you done to get those cycle times really down?
Yeah, so definitely took a lot of times to get to the cycles, sorry. But one of the biggest tips that helped our team during our cycles was to start out slow. So we would basically set our entire drivetrain speed to half speed and practice our pathing going from the submersible to the basket. And then slowly we would keep upping up that number and increasing the entire drivetrain speed so we could get more comfortable with it and more smooth with it.
Great. I think, yeah, as you said, your pathing is really good. Every match, it's almost like you're able to hit those sample cycles really fast. Now, you guys have had an amazing year. I know you guys didn't qualify for the World Championships, but hopefully you guys are going to compete in some off-season events. What future improvements are you looking to add to this already very impressive robot?
Yeah, so one of the biggest future improvements is currently all of these inserts on the box tube are 3D printed, but what we would like to do is to make them metal. So that would probably definitely increase the reliability and the consistency of our box tube mechanism.
Oh yeah, thank you so much, Runtime Terror, for going over this amazing robot with so many mechanically and software complex things. And this is Rahul reporting from the Fun Robotics Network. Catch you next time on Behind the Bot.